Good morning, everyone. Welcome to another episode of Xah Talk Show. Today is 2021, July 20th, 3 o'clock in the afternoon, San Francisco time. And today we are going to do Wolfram Language coding. So I'm going to code mathematics. So let me show you some of the fantastic Wolfram language. So I did this. This is 1990. I wrote this a visual dictionary of spatial plane curves. I wrote this code mostly from 1994 to 1997, most of them. So I haven't touched them for like 20 years, about 20 years. And today I'm going to code some of these. So. But first of all, let me show you some news, okay? Emacs news, Xah Life news. Good morning, Emily. Fantastic Emily. the most technical person in our group. Okay, so we're gonna do, so let me tell you some of the news. I've been working on Emacs, my Emacs website, and Emacs Lisp. I've been coding a lot of Emacs Lisp in the past month. So there is a lot of things I did. So what are we? So let me just go over like for 15 minutes something. Then we're gonna do Wolfram language coding. So if you have comments, questions, post it. Okay. Today's like random chat ish. Emacs. So I want to go through my Emacs blog, tell you what update I have been doing in the past month. And interface change and Emacs distro. Okay, so Emacs distro, let's open that. And okay, let me tell you about Emacs distro. So about a week ago, I did live stream creating this XahEmacs distro. So now it's kind of in shape. So you can just download it and you have, a great Emacs setup. I'm going to work on this for years, probably. This is just a start. The reason I want to create a distro is that, I did a distro before, Emacs, from 2007 to 2004. Okay, about 7 years. And I stopped because no money and, you puke blood, you work on these several hours a day and you become tech support and... But now my life is better. So I created this. I don't want to create another distro because I'm just going to be tech support. Then people are just gonna talk. Oh, how you do this? Oh, XahEmacs sucks. Emacs sucks. They don't. Usually, kind of. Okay. Of course, there are also good news. Like people thank you for it. Anyway. So now I think it's mature. I mean, it's great for me to. I create a Emacs distro. So this distro, so what's the point? The main point is that it's going to be revolving around XahFly keys. Now, XahFly keys is probably the most popular package I've done, and a lot of people use it. So, it has a specially designed key binding. It's like Vim, but however, all the key choices and command map are from a efficiency point of view. On the other hand, Vim is mostly historical. So this package has a lot of users, and it has introduces complete new key binding system to Emacs. But one of the issues is that when you use lots of other packages such as Orgmod, or the most popular, and also the Magit for Git. They have, they follow the traditional Emacs key binding. So if you use those packages, it's not compatible. So you go back to when you are in those major mods, you go back to the, cumbersome Control-C something, Control something keys. So now if I create and it's not easy to create a key system for them all, for all the major packages. So anyway, so the point of Xah distro is, so since I now bundle everything together, I can start to create key bindings for the major mods. So in other words, ideally, this can end up as a systematic key binding system for Emacs in the future sometimes. So, and I'm not going to slave over it. I'm not going to just be tech support and answer other questions. I try my best. Okay, so that's Emacs distro. That's XahEmacs distro I did. Okay, so that, and let's go to XahEmacs blog. So I've been working on my Emacs web tutorial a lot in the past month. So let me give you a brief introduction to how this is like. So the main page, the home page, you have basically 6 major sections, 7. Okay, Emacs tutorial. So just click on them. So you have 7 major entry points. Emacs tutorial, which is all about learning Emacs, the GNU Emacs. Then you have Emacs init. Is about all the details about Emacs init. Many minor mods. What's a major mod? What's a minor mod? What's MS customized? How do you organize your init file? One of the way. There are so many ways. By compile list, what does that mean? Things like that. So this section is about Emacs initialization. Then you have Emacs Keys section, Emacs Keys. So this section is all about Emacs Keys. Emacs, the fundamental part of Emacs is the keys. In fact, that's the historical origin of Emacs Techo, keyboard macro, basically, keyboard macro. So as opposed, this is interesting because in other editors, for example, this is XahTalk Show. Let's open, pink window shows all my commands using XahFly keys and Vorak layout. So I open this, where's the command? Where did I just call it? Yeah, because I open in VS Code. So I open this page, XahTalk Show in VS Code. In many applications in general, in other applications, they are not, the way they are coded is not centered around keystrokes. This is interesting because Emacs is almost the only one I would say probably the only one where it is actually centered on keystrokes. So the first thing you do is keystrokes. Then keystrokes is mapped to command. Essentially, eventually you call a command. Then the command runs to whatever, including, for example, one of the interesting example is, so I'm going to type ABC. So I just pressed 3 keys, and actually those keys are calling the command. Let me show you. Okay, describe key, then press A. You see, so then it tells you. You see, you can tell it tells you that A runs the command self-insert command. So even if you are just typing, it's actually calling a command. It's calling this command. So this is different from any other editors. When you type something, it just you just insert the character. It's not calling to a command to do it. But however, when you press a shortcut, like when you hold down Control or Alt or Control Alt and Command keys, then the application such as VS Code, then they interpret it, then it maps to a command. But Emacs is different. So self-insert command is an example. Let's go back to talk show. So let's today's talk show. Let's insert the things we talked about. Okay. Self-insert command Emacs. Okay, so in fact I can if actually you see all the commands you see on the pink window, but actually it's not showing self-insert because you see A, B, C, D, E, F, G, it's not showing anything here because I actually turned it off. Let's turn it back on so to demonstrate this point. Okay, good morning. Comments? Okay, Braveheart. Okay, so let's let's go to the command log mod. Okay, so you describe function describe function Xah start command log mod. Okay, so you go to these functions source code. So here is the source code for start command log mod. It will actually just create this ping window. So it's calling this command. So you can see the source code is on a Mailpath. Okay, I modified it some myself. So here's the source code, and let's search for self insert command. Okay, so here you have a variable clm log command exceptions. Okay, so the value is a list. So you can see a list. So that this list means any command, if it's any of these command, do not, log it. So you can see self insert here. Why is it? I want to show self insert. Okay. But it's already commented out. Wait, okay, so I'm not. Okay, yeah, I know what's going on. This is actually not the file I'm using. So go to XahEmacs. Actually, we need to talk about Mathematica. So let me quickly see if that can. So here is command log mod, and let's search for self insert. It's commented out, but why is it commented out? Let's search for that again. So search for self insert. Command log exceptions. What's the difference? CLM command log exceptions. Okay, I have a duplicate copy of it. Okay, let's show it here. So you look at the right side so you can see it. Okay, so look at right side so you can see. Actually, I have 2 copies of it. Oh, okay. Oh, there it is. Yeah. So because I modified this file and let's comment the whole thing out. I've been sloppy, so I have a duplicate. So this is the part. So you can see self insert command is, it's there, so it doesn't show. But now let's show it. Okay, hold on a second. So let's go back to, let's comment that out. Then let's set it, evaluate it. And now if I open a new buffer and magnify, if I start to type A, B, C, D, E, F, G, you can see self insert command 7 times. You can see self insert command. So that's a demo of how Emacs is. The implementation of Emacs is very much keystroke based. Okay. I believe that's not the case for basically any application, any other. So, but I want to show you another demonstration. For example, if you type phi, let's say pi, okay, let's say, you see, we got the pi. So you can actually bind a command to that character. You see, it's okay. Let me say this. It's actually not key based. It's character based. Okay, it's character based. Yeah, that's more appropriate. So any other modern application, they are keystroke. They are keystroke based. You can say that. But Emacs is actually character based. But what if you do when you do Control F or something? That is actually also a character. It's an ASCII character. But what if you press, let's say backspace key? That's not a character. Well, backspace is actually a character. Let's say function key, F5. Anyway, I'm getting. Anyway, you can. It's character based. Okay. Let me explain. Let me show you this demonstration. Okay. I can actually bind a key to this character. So global set key. Okay, let's go to Xah Emacs list mod global set key. Okay, so I want the character, whenever I type the character pi, you should do something. Okay, let's see, open a new window. Okay, let's say split. Okay, so what's the command for split? Okay, so whenever I type the character pi, tell Emacs to call the command split window below. Okay, now evaluate it. Now I'm going to let's see how can I let's see, let me try paste. Okay, I don't think paste works. Pi. Okay, I want to demonstrate this, but now I'm running into a problem. How do I actually type it? So I don't think this work neither. Yeah. Okay, let's try a brief. Okay. I have an example on my website, but let's not use my website if we can avoid it. So let's say pi equals to, let's say pii. Okay, pii equals to pi. Okay, evaluate it. So I just defined a brief. So now let's type pii, enter. Okay, that doesn't work. So I mean, what we want is that for Emacs to split window below whenever you type pi. Yeah, that doesn't work. So yeah, okay, so okay, that's a too fancy example, but actually we can show another example. Let's say $. Okay, so evaluate that. Now I'm going to type $, and it splits the window. Okay, this is not a the best example to demonstrate that Emacs is actually character based all the way back to its Techo roots. Yes, and Emily showed me Techo. Yeah, yes, Emily also showed me. She dig into Techo, and she actually installed it on an emulator and read the manuals and demonstrated some very interesting things. Okay, so let's okay, that's about pi. So that's about that. So let's cut that. Let's remove that. I don't want that. Close my brief. Close that. Let's go back to talk show, and let's again hide the self insert command in command log mod. Close it. Save it. Close it. Close it. Close it. Close it. Yes, close it, and back in Xah Talk Show and paste it here. Okay, prettify and show in browser. Okay, I've been talking for how long? 22 minutes. Okay, I'm gonna get to Mathematica in just about ready. Okay, so Emacs tutorial. So then Emacs init. Then you have everything about Emacs Keys. Then you have practical Emacs Lisp tutorial. Then you have Emacs Lisp examples. Then more Emacs Lisp. And this section is about how to write a major mod. So it's kind of a bit more advanced Emacs Lisp. So that's the main 7 sections of my Emacs website. Now, so I worked on a lot of it before today. You will see lots of the main Emacs tutorial section on the side panel. You will see a lot rocket symbol. Okay, so where's the rocket symbol? Let me show you. Okay, well, you will see a lot items here. That is my custom Emacs Lisp code to enhance Emacs. But I moved them now to the elisp examples section. So there are about 20 of them I moved here. So this way, I hope it's more clear, so that when you people read the Emacs tutorial here, you are just learning the the fundamentals of GNU Emacs. But when you are, when you want to extend your Emacs to make it more efficient and so on, you can go to the Emacs Lisp examples. So everything here is Emacs Lisp code. So let's see. So for example, so open file fast, direct sort file by time or by size, rename file, space to hyphen, just press one key and a file is let me show you that, okay? So for example, I create a new file, something, this, that, okay? Something, this, that, copy that, save it, something, this, that, .txt, okay? So you can see the file, and I dive into the directory. This is a file, magnify. Now, you see there's a space. I want to change them to underscore. So all I have to do is press one key, press it, then the file is changed. Normally you would have to call, let's hide the details, okay? Wait, hide detail is left parenthesis. So normally if I want to change the file name of this file, you have to call this command, dired toggle read only, see? Then you can change, okay? You can change. Then basically you call query replace space by underscore, enter, wait, I typed it wrong, space by underscore, enter, yes, 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 okay? So once you are done, then you press CC to call write dired finish edit, okay? Then the file name is changed. Yeah, but now I can just press, with this rename file, space to hyphen low line command, I can just press one single key. So saving keystrokes is all it's about. Okay, so let's open that, delete it. We don't need this file. Refresh, so it's automatically deleted and also made a backup. So that's another command you'll find here. So that's these. Okay, so let me show you some examples. I search current word. Okay, I search current word. This is an enhanced command to search the word under cursor. Now, Emacs also has that, but actually it's not so good because I explained search text. So this section is everything you want to know about search text in current buffer, or find and replace in current buffer, or in a directory. Okay, so this section, all the details you can read about, or highlight text, and so you can search current word, but however, Emacs so you use these commands to search current word. I search forward symbol at point. The default key is Alt S then dot. But one of the problem is that it checks boundary. That means if you have a text with XY2 and you try to search XY, the XY2 will not show up because the 2 is kind of the boundary. So this version, the Emacs version, is useful if you are coding, in programming languages. You sometimes it's useful that way, but most of the time, for me at least, when I search something, I want every string that contains those characters. I don't want, checking boundaries. So that is why you have, this command, I search current word. Okay, and so on. So that's what I worked on in past month, especially yesterday. I worked on and also some interesting things. I updated. You see this screenshot. This screenshot must be this screenshot is about 10 years old. I updated a lot of screenshots to usually it doesn't matter because Emacs is still the same, exactly the same. But however, just for a change, sometimes you want, so now I have new screenshots. Now before it was, this is on Linux, this is 2010 or something. And now, For example, I have it on Windows, and some of the old screenshot is on Mac, for example. So let me show you the interesting screenshot because that's interesting. Okay. So you need to go to Emacs, go to diode, go up directory, and go to this directory unused. Okay, this is unused images. Okay, so now you open them. Show in desktop. Okay, that's a command. Then you can see, this is on a Mac. This must be 12 years old screenshot. And this is on Windows Vista. This must be 2009 or something. And, it's interesting because when you look at your old screenshots, you'll notice the minor differences in changes in Emacs. For example, today it doesn't say like that. The wording changed a bit. Then you have this screenshot is on Linux, and this one on the Mac. Yeah, this must be 2007 or something. Another one on Linux. Interesting. Yeah. So also here, this is the menu from Emacs diode. Okay, ed. You notice that the keystrokes are in parentheses. Not any longer. So we are in diode. Let's look at, let's see mark. Okay, mark menu. You see the keystrokes are no longer in parentheses and they are right aligned. So it's actually better slightly. Okay, so that's some of the random talk. Oh, and this screenshot is new. Okay, they updated. And this screenshot is also 7 years old. I haven't been using Linux for like 7 years. So every time you see my Linux screenshot, those are at least 7 years old. Okay, I want to, and also in Linux, I have, used different desktop Windows managers. So some of them are in XDFC, XFCE, I don't, I even get the wrong names wrong. And some of them are in different, systems. Anyway, let's forget about that. So let's talk about Wolfram language. Okay, so I want to do, so it's just random coding. Okay, so I'm not going to, so there's no plan. I'm just going to do some live coding of Wolfram language, just show something interesting maybe. Okay, so that's what I've been doing with Emacs. Okay, that's enough about Emacs. Okay, so let's go to Wolfram language. Okay, let's do the Visual Spatial Dictionary of Plane Curves, the famous Emily. Yes. Yes, so yeah, good morning, Fazing. So let's do some mathematics, Wolfram language. Okay, so let's go to, what is this? Emacs block, close the directory. What is this talk show? Close, go to eblock. No, let's go to desktop. Go to documents. Okay, open external. So Wolfram language. So let's open that. I don't know what I want to do. I just know I want to update some, start to code these. So let's see, let's pick something. So, you are looking at the directory. This directory is basically half of my Wolfram, most of my Wolfram language Mathematica packages. For example, let's look at plain tiling. So that's plain tiling package. So this, this is pretty old. So 1998 I wrote this, and last update 2016. Not really. I didn't really work on it. So 2016, I only worked on it for 2 days because, so you see this package draw, you can just say wallpaper plot and give it a number, and it will plot it, and you can say how many copies of it. So what I need to do is actually I need to update, to make these compatible with the latest version of Wolfram Language. In fact, I think, if I just try to run the code, so you can see here is more fancy Wolfram Language code. You got fractions and so on. And here is the illustration of all the 17 wallpaper groups. So this is part of group theory. These things are called wallpaper groups. Okay, they are just called wallpaper groups. You can just look up on Wikipedia. So they are illustrations of their fundamental region and their symmetry points. So what are they exactly? You see, when you have a carpet, or when you have a carpet or a tiling on the floor, you see there are many symmetries. So mathematicians can study it and can create a specification for the symmetry of a particular pattern. So it turns out the total number of possible, symmetry, the way they are symmetric, is only 17 for wallpaper groups. So mathematician gives them an ID for each of the symmetry groups. Okay, so since we are talking about that, let me show you this this project I did like 23 years ago, 1997. This is one of my most cited project. Okay, so the 17 wallpaper groups. Okay, so mathematicians has a given notation, Overfold notation. This is invented by John Holton Conway, who died 2 years ago due to COVID. One of the mathematician died. One of the early person died from COVID. So he's a mathematician. I admire his work. So Overfold notation is a notation to describe each and every of the 17 possible wallpaper groups, symmetry. So so then you have the crystallographic notation. This is more traditional. So what's the difference? You see, the crystallographic notation is kind of mnemonic based. It will take some time to explain. But anyway, so why did Conway invented the Overfold notation? The Overfold notation is because this notation gives, just by reading, their identification, just by reading their name, they give more information about the symmetry of that type. Okay, so that's why the Overfold notation. But the crystallographic notation is already well established by, used in crystallographic. That's essentially the analysis of crystals. Okay, so for example, anything I'm talking about, you can go to Wikipedia. Wikipedia has, tremendous information. Crystallography basically is the classification and identification of crystals such as quartz, or in snowflakes, in sugar structure, things like that. I don't know much about them. Condensed matter physics. Okay, so so here is kind of illustration of what they are like about, basically the structures. And this is a 3D case. Now, when we talk about wallpaper groups, that's a 2D case. So let me show you. So these here are the 17 wallpaper groups. Wallpaper gallery. Okay, so So first of all, let me show you the 17 possible wallpaper groups. So you are looking at a example of each of the possible wallpaper group. In other words, each of these wallpaper represent a specific symmetry type. So you can see here's a wallpaper. So what defines a wallpaper? Essentially, it's something that repeats, okay, a pattern, on a floor that repeats. And mathematicians has to classify how are they symmetric. So this one, and then you see this diagram. This diagram illustrates how it is symmetric of this wallpaper, okay. So you can see another one. Where is my, okay, next. Let's go to next. So here's another one. Here's another one. So this one, you have a red line, double line there. That means there's a mirror reflection symmetry. You see there's a mirror reflection on each of the line, but there's no vertical reflection. Then you also have this that L-shaped thing. That means it's a translational symmetry. Okay, that means you can move part of it and move forward a bit, then the whole thing is exactly the same, just repeat. Okay, so then then you have several others. So you have this, now you have this kind of thing. Now this kind of thing, one way to put it, to explain it, is like footsteps, footprint. So like when you walk on a sand, you have this kind of symmetric pattern. So, and again, there are 17 possible 17 possible symmetry patterns, no more and no less. That's how mathematicians proved it. And so in my project, I proved part of it, okay? So derivation and classification of groups, okay? So yeah, so then you get prettier, then you started to see some of the more prettier patterns, symmetries, okay? Now, in all these examples, what I use is a star, a 5-pointed star, to demonstrate all the 17 possible patterns. So each one of them, all you see, the motif is just a single, one or more stars, 5-pointed stars. So again, you can go to Wikipedia wallpaper groups. Then they have lots of other examples. So all these are done with Mathematica. This is you run this code and you will generate this illustration. And okay, too much. I wanted to actually code. I haven't started to code Wolfram Language, so I just explained the whole thing. So, is it any comments? But I've got my server turned off. Yes, Emily. Sounds crystal clear to me. Very much reminds me of researching tessellations and patterns associated. Yeah, I'm very much into this, and I'm getting old. But one of these days, if I want to revisit. Okay, let me show you some of the patterns. Okay, for example. So you see you can generate these Islamic tilings by giving one pattern a fundamental. You can see the illustration here. You can just find the geometry, the locations for each of these points, and just draw that. Then you can call one of the command to generate the entire wallpaper, and you can also generate random ones. You pick a specific symmetry ID, then you just say, okay, use this pattern and generate a symmetry of that. Then so this, I did this long ago. I want to I'm interested, and I want to write them in JavaScript as well. And first of all, I need to update this Wolfram language code. I've been delaying them. So Yeah, so these are very interesting. So so I haven't, so the question to myself is that should I, actually start to code some, code Wolfram language, or start to talk about the mathematics of it instead? Let me just talk mathematics about it, something about it, because if I start to code Wolfram language, I'm not, really ready. You're gonna see a lot stumbling and stuff. So patterns, so study of symmetry, there are quite a lot very interesting things about it. Not just wallpaper groups, okay? So yeah, so let me give you like non-professional account of the interesting things about symmetry and symmetry groups, group theory, and tiling theory, and patterns theory, and so on. Related things, okay? But before we do anything about that, yeah, there's quite a lot of interesting things, because there is also okay, look at this one. This is a fractal based, okay? This is fantastic. In Wolfram language, everything is scalable. It's a PostScript. The image behind it is actually encoded in PostScript, so it can scale to any size. So this one, you might be wondering. So first of all, we talked about. So we have been talking about the wallpaper groups, right? Which is the classification of the two-dimensional symmetry patterns. Now you can go into. So it's part of the study of crystallography, and you can go into 3-dimension. Of course, crystals are in 3-dimension. In 3-dimension, I believe the possible symmetry groups, there are 270. Okay, Wikipedia will say it somewhere. Okay, I believe there are 270 of them, and it is my dream since like 20 years ago to actually write a program to visualize the 270 possible 3D crystallography groups. That would be amazing, especially in today's technology. Game, you guys gamers, 3D games, you can do that. So imagine you can fly, in a 3-dimensional space. You can fly through any of the 270 possible crystallographic groups in 3D. So I wanted to do that. I just never get to. I hope I will do it, soon, someday. So 3D case. Okay, so as far as I know, I have not seen. Yeah, I don't ever, even although I haven't looked for the past like 15 years, but I have never seen someone actually do it. So here's a project. You guys young people might do it. Write a program just like the 2D case, but write a 3D case so people can fly through each of the 270 crystallographic 3D groups. What's the proper name? Let's search the proper name. Okay, I want to group symmetry subperiodic space group. Okay, so it's called space groups. Yeah, so there, we talked about wallpaper groups, but there are quite a lot very much related things. Okay, yeah, so you can see all the highlighted here, they are all related. Okay, now point group, it's very interesting. Let's open that. Space group, very interesting. Let's open that. Okay, hold on a second. Let's magnify. Okay, go back. Then symmetry group, that's kind of related. Okay, but let's not open that. Let's crystallographic point group, then crystallographic group. Okay, those are very interesting things. Okay, now point group, yeah, so you started to see the point group symmetries. Okay, so what's the difference between point group and wallpaper group or the 3D crystallographics group? Well, essentially point group is only consider a point. So for example, when we have wallpapers here, these patterns, they are not points. But if the only possible figure is allowed is just one single point, then what are the possible symmetries in 2D or in 3D, or in 4D? They can go on to higher dimensions, 4D, 5D, 7D, higher dimensions. So if you allow the motif to be just a point, then what are the possible, symmetry groups? That's a point group. Okay, let's read it just to double check. In geometry, a point group is a group of geometric symmetries that keep at least one point fixed. Okay. Okay, I might be wrong. Point groups can exist in a Euclidean space with any dimension, and every point group in dimension D is a subgroup of orthogonal group. Okay, point groups can be realized as a set of orthogonal matrices M that transform point X to point Y. So that keeps at least one point fixed. Did I get it wrong? Cairo and Cairo. So, Okay, I think I might be wrong in my explanation. What I was talking about is actually lattice group. I don't know. So don't take my word for it. Read Wikipedia. Meanwhile, I think the point group is just basically you just have one point in the center. Okay, so this goes on, but I can know for sure if I take 5 more minutes to read it. Let's not. Okay, point group is very interesting. Then space group. Okay, yeah. So this is very interesting. Space group symmetry. So one of you, as a project, go write a program in maybe JavaScript or in Wolfram Language. You can download it. You can use Wolfram Language. That would be easier. That would be 10 times easier. But the problem, if you use Wolfram Language to write this program, the problem is that you cannot, you require the Wolfram engine to run. But however, it would be nice to play this as a game. Like you can tell other people to go to your website and fly through this three-dimensional space with these symmetry structures. So that's interesting. In order to do that, you can use JavaScript, WebGL. That's probably the easiest way. Or you can, if you know about programming games, you can use a game engine. I believe that's possible. Yes, since we are talking about Euclidean space. So I would, that would be my dream. Okay, that would be my dream for 20 years. Someone, you guys, okay, Emily, Emily would be the best, most suitable candidate. Oh, Justin Scarfi. Justin Scarfi is a mathematician, a professional mathematician. Are you in fact, he's a professor, right? Haven't seen you for a long time. How are you? So Justin Scarfi, but Justin is not a coder, okay? so one of you guys, or maybe Bart, okay? One of you guys write a program in a game engine, okay? Unreal Engine, there's lots of game engines, I don't know how to. I tried, but you go write a game engine, write a program in a game engine using WebGL whatever to fly through a space group structure of order 230. Okay, so it says here how many there are space group. Okay, in math, physics, and chemistry, a space group is a symmetry group of a configuration in space, right? Usually in 3 dimensions. Okay, in 3 dimensions there are 219 distinct types, or 230 if chiral copies are considered distinct. Okay, chiral, that's another very interesting concept. Basically, it's a left-right mirror. Okay. Space groups are also studied in dimensions other than 3, where they are sometimes called Bieber-Bach groups and are discrete co-compact groups of isometries of an oriented Euclidean space. Okay, fascinating. This group theory, that's what I love. Okay, unfortunately, math is my true love, but she has been difficult. Okay, and there you see the overfold notation we talked about. Let's open it. So reading Wikipedia is what we do. In geometry, overfold notation is a system, or overfold signature is a system invented by mathematician William Thurston and promoted by John Conway. Oh, it's invented by William Thurston. Oh, okay. For representing types of symmetry groups in two-dimensional spaces of constant curvature. Okay. That's the detail. So you have wallpaper groups we talked about. In 20 years ago, my website is almost the only one that talk about this. Then Wikipedia becomes better and better and better, and Wikipedia now has lots of examples and explanation in detail. So you can see actual patterns in real world demonstrating some of these symmetries. Okay, and there are other sites that photographs of actual tiles on the floor or carpet and things like that. So Wikipedia, go check it out. So they also have a diagram similar to mine, but I didn't invent it. Of course, I read it somewhere else in the literature. This diagram is used to illustrate the symmetry of a wallpaper group pattern. So those of you interested in math, you might want to check it out. Very interesting. Wallpaper symmetry groups. Okay, overfold notation, symmetry groups, then crystallographic point group. So point group is what we have been talking about. Yeah, exactly. That's what I was trying to explain about point groups. Okay, so there you have it. Then you have space groups we talked about. Why is it two? So crystallographic group is the same as space group. It's a alias. Okay, it's the same thing. Okay, so that's about that. Okay. School makes you smarter. Okay, so we talked about an hour. Maybe that's it. So back to the interesting things related to these wallpaper groups, or the patterns and symmetry and tilings. There are so many theories from different aspects. Okay, so we talked about the symmetry group, basically patterns, symmetry groups of two-dimensional space, three-dimensional space, and higher. And also we talked about if we do not allow shapes but just points, what happens to the possible symmetries. Okay, so there are different considerations. So that's why you have all these kind of groups in math. Okay, now of course you guys go read my page. Okay, since I read my page, introduction. This is real math. Okay, this is real mathematics. You consider it undergraduate, third year or something. Then theorems about rotations and translation in a plane. Then the discontinuous groups. Okay, then you learn some of the concept, fundamental region, and what does symmetry means, isometry, and so on. Translation, reflection, transitivity of translation, that's a theorem. Then twofold rotation on midpoint of a lattice. Okay, that's and by the way, there's a theorem. Okay, there's a theorem. For example, there's a question: is it possible? You see all sort of patterns in tiling or stuff. Have you ever seen one that's five-fold rotational symmetry? So this is six-fold. That means this is threefold actually. You see those triangles. So you rotate it by by 120 degrees, you know, 1/3 of a clock, then you repeat the pattern. And there are also so this one has many six-fold rotational symmetry. Now the question is, to mathematicians, have you ever seen, is it possible to have a pattern that's a five-fold rotational symmetry, you know, like a pentagon? You know, so mathematicians try to do that, so it turns out no, it's not possible. And then you can read about why, you can prove it is impossible from this theorem, okay? Theorem, crystallographic restriction, okay, that's the name. You can see the proof, and I believe there's a Wikipedia article, I believe, yeah, crystallographic restriction theorem, okay, so they also explain it here. You know, lots of math. Then you have, okay, higher dimensions. Okay, they actually go into higher dimensions. So okay, so apparently it's not possible in higher dimensions neither. So there's a lot of math, you know. Yeah, that's why I love math. Okay, math. So so what I want to say is that, yeah, so the symmetry of a pattern in n dimensions, that's one thing we've so far talked about. Let's talk about some other interesting things, and that'll be it. 10 more minutes maybe. Comments, okay, comments, guys. So let's talk about, you know, if I'm being too repetitious, just say it, okay? Like, tell me, like, say whatever you are interested in. Justin Scarfi, say something. How is Canada going? How is your health? Okay, so I want to say, so symmetry aspect, that's one interesting thing. Let me talk about some many you know, other interesting things, okay? So for example, this one. So if you look at this pattern, okay, let's go show Mathematica. So if you look at this pattern, first of all, we can analyze this pattern by symmetry, just we did before. So if you are a mathematician, you look at this, you can say, oh, so there's a symmetry point right here, that's a six-fold rotational symmetry. And also right here, there's a vertical line, mirror symmetry. There's also, you know, basically there are six lines of vertical symmetry, mirror symmetry, right? Reflection symmetry, okay, on each of these points. Then on here, same thing. So you can see on this pattern, if we go back to the, you know, on this pattern, if we go back to wallpaper groups, you can, you know, we can find out what the symmetry it is. Let's see, is it this one? Okay, that's only, okay, that's six-fold, so it's probably that one. Then in the middle, it's three-fold. It's like, okay, this one doesn't have reflection or symmetry, okay? So it's not this one. This one, okay? So we are saying that this pattern probably has the symmetry of this one. Now that's homework, okay? you look into detail, check if this pattern is the symmetry of that one, okay? Now you can find that one on my website here, somewhere here. Here, this one, okay? There is a URL there. Yeah, so, okay, so from the symmetry point of view, but you can, you know, that's one interesting perspective aspect. But then another point of view is that the way this graphics is generated is actually by what you call, by fractal means, okay, by nesting, by what's the proper name is called, I forgot, yeah, what's the name, LFS systems, iterated function systems, IFS systems, okay? It's kind of it's a fractal, okay? Or you can also do it by Turtle Graphics, you know, with the logo programming language, which made the concept of turtle graphics famous. Okay, so let's go to let me just show you some of the. Okay, turtle graphics. Okay, they also came to Python, but it was made famous by the programming language called Logo. Logo is a dialect of Lisp invented by a Lisp expert. Okay, he's in Berkeley. He's in Berkeley. But anyway, he created a Lisp variant, but without the parentheses, called Logo. And the intention of the Logo programming language is to teach children about programming. But essentially, it's a Lisp. Okay. So I want to go to Turtle Graphics Wikipedia. So this is in 1980s. Okay, Logo programming language. So they made the Logo graphics, Turtle graphics, very popular. Okay. So basically you have a turtle that basically a pen. You say where which direction to go, when to not draw, things like that. L systems. Okay, the name. Yeah, the name I'm trying to think of is L systems. Okay, so you can see a lot of math is going on here. So L systems, Lindemann Meyer system. It's a system to generate iterative graphics originated from the study of plants. Basically, you guys programmers would be interested in this because it's essentially based on recursion. Okay, you scheme these fans, recursion. Okay, so you can generate, you can see all these. Then it's then you can study the fractal dimension of these images. That's more advanced math concept. Okay, don't ask me any math because I don't. I'm not that good. Okay, so but I want to show you some of the other things I've done long ago. Okay, so let's go to my website. Let's just go to Xah Math. Okay, Xah Math. Go to my home page. Then let's go to the math software. Okay, so open math software. So these are fantastic, all sort of software doing visual mathematics. Okay, I mean beautiful and fun to use math softwares with high real math. This is not for children. Like typically you see, for example, you see people talk about math. Usually it's for children and it's idiotic squares, triangles. Oh, you put this triangle here. That's idiotic. Okay, what you see here is beautiful. It's fun. It's easy to use, and it embodies real math, the advanced PhD mathematics. Okay, many of them embody there's a lot to study about them. For example, here you have Go, you have 3D Go on different topology background. Then you have hex, so you getting into game theory depending on how deep you want to go. You have Chinese chess game theory. Okay, game theory and algorithmic zero-sum games, algorithms to play games, or AI, depending on how far you go. You can create a neural networks to play these games. Of course, Google did it 3 years ago. Breakthrough, they, AI beat humans in playing Go. So that's one thing. Similar for others. There are a lot of math. For example, before I talked about flying through three-dimensional structures. Okay, here is one of such program written by Jeff Weeks. Okay, Jeff Weeks is a mathematician. He studied cosmology. He's a cosmology specialist, and he has written books. Okay, The Shape of the Space. I have this book. I read it like in the 1990s mostly. Great books. Okay, go buy it. So I want to say shape of space. Let's turn on JavaScript so that we have okay. Then this is actually a program, so you can go to his website and download it. Okay, it's available for Windows, Mac, and Linux. Okay, shape of space. This is pretty old, 20 years ago, and he has updated ever since. curve, basically, normally we are familiar with Euclidean space that is flat, just like a piece of paper. Euclidean space, we imagine it's just straight, it's not like curved, it's not like a flag, so it's straight, it goes to infinite dimensions. And in three-dimension space, we have normally, intuitively, we think of our space as Euclidean, meaning it's just flat. You can go in any direction, infinite direction, further away. But it turns out mathematicians discovered it's actually, there are different type, different topology, different shape of our space. So, but it's impossible to imagine. So here you have a curved spaces in 3D, okay? All these are three-dimensional. In math, you have the dimensionality, 2D, 1D, 3D, 4, 5, 6. Then you have more complex concept of fractal dimension or infinite dimension. But anyway, given a dimension, you have a geometry, okay? You have a topology, you have a geometry. So here in this program, we are talking about three-dimensional space, just like our world. But actually, they show you different shapes. Actually, there are different shapes. Some are so weird that if you go straight forward, you will come back to yourself. If you live in one of the such, three-dimensional space, if you have a infinite powered binocular or telescope, you will see back of your head. So that's a topology of space. Okay, I rambled over. I wanted to show you the fractals. Okay, we get back to tiling. Okay, so yeah, fractal curves and L systems. So these programs are old actually. Yeah, these are old 1990s Mac OS programs. Now, I removed the link, but you can still find the link in, where did I, in old math software here, I believe. Okay, these are, I've been obsessive about this kind of software since 1990s, and I kept updating them, but essentially I stopped around 2005. So many of these programs are dead or old or no longer maintained, so I put them into this page. A lot of them are Java, but Java no longer runs on the web. Although it's still possible to get them to run. So there are many of them tilings or for, and some of them are Mac or anyway. So I want to say, yeah, back to, so that's all I want to show. I wanted to show you these L systems, okay? The best source to study them is beginning with Wikipedia. So just go to Wikipedia. I showed the article before, L systems, this page, okay? So that's what I'm saying. So this image, aside from the symmetry point of view, you can also study, as a fractal, as a L systems. For example, how many possible ways to create this image, or exactly what is the, the way I coded this is by line transform, So actually, let's see the code, okay? GP, where's GP? Okay, there it is. So I began with this grid, okay? Then, so this grid is just a bunch of lines. Then for each line, I transform them into this kind of shape. Then after after 3 steps of recursion, that's what you get. So, it's fun and interesting. So fractal, so L systems, recursion and generation, that's another way to look at a pattern, a two-dimensional pattern. Another way to look at two-dimensional pattern is from a tiling perspective. So tilings, okay, so tiling gallery. Okay, so how do we discuss about that? For example, you have all sort of toggle contrast, so you have all sort of tilings, and let's see if we can actually, you can magnify that. So tilings, so when you think about tilings, they are not just symmetry. Of course, for each one of these image or tiling, you can consider the symmetry aspect and identify, which one is it. But there is also theories about tilings. For example, let's show an example. For example, this one is made, this pattern is made up of a single shape. You see this triple arrow? So you have this is called prototile. Okay, so if you imagine actual tile, you can, or you can use paper and cut it. So you can use this one single shape to tile the plane. So the question is, what are other shapes that tiles the plane? Somehow is it, so, or another way to say it is that given a shape, how do you know it's gonna tile the plane or not? So you have to do math. You have to start to create theories of math. So, and that's another very deep topic, okay, tiling and patterns. And this one is another thing. So for this one, this pattern, for example, you can look at it from a symmetry perspective. You can also look at from a tiling perspective. So if you look at from a tiling perspective, you see, so the white thing is a tile. Then this rhombus shape, that's another tile. Then this you have like these three different tiles of the same shape, colored red. Okay, then you don't think of them as links, rather you think of them as separate pieces. So then you think about the tiling aspect. But another aspect here is linkages. So when we look at this, we naturally think of the red are just actually a circle. It's a link of a particular shape. So when you think about them as linkages, then that's another theory. That's not theory and not theory and linkages, link theory. They're very interesting. Okay, so let's show another one. Okay, that's about that. Okay, I think that's it for today. How many people are watching? 9 people. Okay, we're gonna stop after 5 minutes. Okay, let me run the Mathematica code to see if they actually run. Okay, so I haven't been running this for a long time. Let's run it. So first of all, okay, so I want to go to the top. This is my PO box that's like 20 years old, dead, like 10 years, 15 years dead. So let's try run it. Okay, plain tiling, run it. Do you want to automatically evaluate? No. Cannot open plain tiling. Okay. Okay, so it cannot open. Let's open this one. Okay. So here is the source code. Let's show you. So this is comment. All these are comment. Then here you begin to have source code, unprotect something, and unprotect symbols. So again, Wolfram language is just like Lisp. Okay, so unprotect means, why do I want to unprotect? Because just in case I already evaluated this, so I want to, because actually I protect them later. Yeah, you can see the code down. You can see all this code, protect. Protect means do not allow any change to these symbols definition. That's what protect is. So if someone run the code, then they will not be able to modify, or redefine, let's say, star motif or translate 2D graphics. They will not be able to. But if they want to load this package again for some reason, then you need to unprotect them, because, in order to make change to them. So anyway, so here's a code. Then you have lattice coordinates. Then you have, let's show some of the main code. Okay, let's show some interesting code. So here we begin to see some interesting code. Let's shrink. Okay, let's shrink so we can see. Okay, that's too big. Okay, so anyway, I want to run no code. Okay, this is a package. Let's run it. Oh, okay, so is there any error? Fantastic, no error. This is 15 years old and no error. Wait, is that true? Oh, fantastic. Now I can run these pretty graphics. Okay. Let's try this. Do it. Oh! Let's try this. First of all, let's delete the image. Okay. Delete it. Run it. Oh! My code works. Okay, let's try some variation. Okay, let's change the parameter. Okay, we want to try some variation. Plot point, let's say 16. Okay, 16 is a different type of symmetry. Do it. There you have it. So in this example, the motif is a L-shaped thing, and now we are generating two different wallpaper with it. So let's try 15. Okay, 15, then it's gonna be something different. Let's try 9. Okay. Okay, so there it is. Let's try this one. Okay, this one was interesting, beautiful. Now let's try 16. Let's put it code here. 16. Okay, do it. Oh wait, do it. Oh, okay, 16. Then you got that. Then let's make it more copies. Plot point 9. Okay, so let's see what we got. Okay, interesting. Okay, anyway, the code runs. Fantastic. That's it for today. Thank you guys for watching. Wolfram seems to be the opposite of Python. It just works. Even after decades, with Python, you never know. That's true. Yeah, it's one of the things Stephen Wolfram is very proud of. He would say, my language after 30 years is still, the version 1 code still runs, mostly. Yeah, vast majority of it. True, because in order to do that, you have to, in order for this to happen, we are talking about language design. You have to be very careful. You have to have like a very good vision. Yeah, which he does. You have to have a very good vision in what you want in your language. And also, in Wolfram language, there are some, let's say there are some advantages. Because when you do high level, when you design a high level language, very, very, very high level language, then it's more possible to have a language that does not change after 10, 20, 30 years. Okay. But if you are doing low level language, that's more difficult. Okay. Yeah. Okay. So I demonstrated my code. It still runs. And what is there anything else? So for example, this one is illustration of the, of one of the symmetry. A hexagon means at that point there's a 6-fold rotational symmetry. A rhombus means there is twofold rotational symmetry there. And a double line means there's a mirror symmetry. A triangle means there's a threefold rotational symmetry. So if we change this to 16, let's see a different, there. So this is type 16. There is no mirror symmetry. Okay, so that works. Great, I'm actually very happy. I'm quite happy my code still works. Yeah, that's it for today. So that's that's close to 90 minutes. Okay, so thank you guys for watching. Bye guys. Oh yeah, last thing I want to mention, Wolfram Language is free. Okay, so you just go to just search for Xah Li Wolfram Lan. Okay, then you go to my page and you go down. I have several videos and tutorials more focused on teaching you Wolfram Language Mathematica, which I did 2 months ago, 2 or 3. Then you have Wolfram Language download for free. Just go to this page. It's free. Okay, the engine is free. Then I want to so I started to write a tutorial. It's a mess. I haven't done yet. But I started to write a tutorial for Wolfram Language. Great. Thank you, Bart, and thank you guys for coming. Bye. Oh, now I have 14 people watching.